Alright, this is Mr. Gohm, and today we're going to be taking a look at some linear models and interpreting some of that data. And again, we're going to start with a little vocabulary just as a refresher here. A linear model is a bivariate graph with data trending in a straight line. Okay, that's a fancy way of saying bivariate. It just means two variables. Okay, so in this case an x and a y, and it trends in a straight line on a coordinate plane. The variable x is represented on the x-axis, and the variable y is represented on the y-axis. And so an example of a linear model would be a model that goes in a straight line. Okay, there's two types of linear models. There's four types of linear models, but the two that we will be looking at will be the increasing graphs, which is in red here. This is increasing, goes from bottom to top. Looks like it's climbing uphill. And then there's also what we call a decreasing graph. It's going from top to bottom. So if I had another model here, x and y, it would be decreasing. Okay, and so for this section, we're just going to really be looking at the increasing graphs and the decreasing graphs. Okay, but they are both linear because the data follows a straight line. One of the big points I'm going to try to emphasize today has to do with the types of variables. We call the x values independent variables, and we call the y values dependent variables. And just keep in mind that graphs are always composed from a series of ordered pairs. And so any point on this graph can be represented by an ordered pair. Its position can be. All right, so for example, and I really want to stress this, independent is x and dependent is y. So for the first graph here, if we take a look, I'm unable to type into the t-charts that are on your paper, so go ahead and pause the video for a second and write these values down, because I would like for us to figure out what the missing values are by looking at the model. All right, I would like you to label independent, and this is dependent. And I want you to do that because whatever this graph is representing is saying that as the weight changes, the price increases. Because you can see that this would be an increasing graph. It's going from bottom to top. All right, it's going from bottom to top. If you read it from left to right, it's going from bottom to top. It's increasing. So this might be the example of like when you go to the grocery store and you get something. Well, this is in kilograms, so I guess the grocery store wouldn't be a good example. But as the weight increases, the price also increases. And so it's an increasing graph. Depending on how much weight there is, depends on what price you're going to get. So maybe you could do like, if you watch the History Channel and you watch the tuna hunter people, maybe they have tunas that are different amounts of kilograms, and as the weight of that tuna increases, that depends on how much money they get for their tuna, along with some other factors, but you get the idea. So the price depends on how much it weighs. Okay, so we always try to put our independent variable along the x-axis and our dependent variable on the y-axis. Okay, independent x, dependent y. And so you really just have to read the context of the problem to determine which one depends on the other. All right, when I look at this graph, I see 0, 0. We already have 0, 0 on our graph right here. Remember, these are all representing ordered pairs. Now I'd like to know what the y-coordinate is when x is 5. Well, if I look at the x value of 5 and I look at where the y value would be, I know it would be at 100. So I could put a value in there in my t-chart of 100 because that's what this graph is representing at the point 5, 100. And then again, I could look at 10, and I could decide what my y value would be. It looks to me to be at 200. And it works the same way with the y values. Okay, now that I'm in the y column here, I can look at the y value of 300, and I can decide what the x value would be. Looks like it would be 15. And at 400, for the y value, it looks like the x value would be at 20. All right, and so you can kind of see that I'm pulling these points, these data points, just from where the line is. The linear model is representing the points are at. So in this case, 500. You'll also notice that if we're talking about a linear model, there's a pattern in the graph. So we go 0, 5, 10, 15, 20, 25. It's a pattern. It's increasing by 5s. Okay, so if it's linear, it'll be a constant rate of change. That's something we talked about yesterday. Same way with the price. It goes 0, 100, 200, 300, 400, 500. Okay, and so you can always pull data points from your linear model as well to fill out your t-chart. So let's practice again. This time we have a decreasing linear model, and again this is the independent and this is the dependent variable. Okay, up and down and left and right. So x values are independent. These are the y values that are dependent on this y-axis. So let's take a look at this, and I picked some numbers here again. Let's see what y is when x is negative 3. Looks to me like it's at 5. Okay. Now let's look at the x value when y is 3. So if y is 3 right here on this point, on this line, we didn't move left and right at all, so we'd be at 0. When the x value is 3, on the x-axis, we would go over 3, and I see that my line is at 1. It's at 1. And again, my y value this time is at negative 1. Looks like my x value is at 6. And it's pretty obvious that this is a linear model. It is decreasing. I guess we could write that on there too as a reminder. It's a decreasing linear model. It's going downhill from left to right. And this is how I'm going to take the coordinates off of the linear model into my t-chart. And we're going to use those coordinates here in the near future for some additional exercises. Let's take a look at this next one here. And again, we have an increasing model. Increasing. This guy is the dependent. This guy is the independent. Okay, x and y. Sorry, get those backwards. Independent and dependent. Okay, x is independent and because y depends on what x is. So if x is negative 2, then the y value would be negative 6. If x is negative 1, then y would be negative 4. Other way around now, if we look at a y value that's at negative 2, we would go to our y-axis at negative 2, and we try to find our x. In this case, it would be 0. When the y value is 0, up and down 0, it looks like the x value would be at 1. When the x value is 2, boom, boom, on the x-axis, I see that my line is at positive 2. When the value is 3, I see that my line is at the value of 4. When my y value is 6, it looks like my x value is 4. Okay, and so we're just taking the position of the line at each of those coordinates and finding what the missing coordinate is by looking at the linear model. And now we have another substitution exercise. Okay, we have bivariate data, meaning we have two variables, and so in our equation we have two variables, the x and the y, the x being the independent and the y being the dependent. All right, so y depends on what x is. All right. In this case, if x was 1, let's just practice our substitution skills. Where the x used to be, I'm going to put an empty parentheses. I'm going to take out what I know x to be, and I'm going to put in the value that I'm wondering about. So in this case, 1. Y equals 3 times 1 is 3 plus 1. So y equals 4. So the y value is 4. All right, so basically we're just solving this one-step equation, but we already had the value that we're looking for all by itself. We just need to simplify. Again, let's do it again. Let's this time we're using the same equation. There's two variables, and where the x was, because it's in the x column, so 2 is in the x column, I'm going to put the 2 in for where the x used to be. Y equals 6 plus 1, or y equals 7. All right. Now we have a little change of pace here. Now we're in the y column, and we know the y value is 10. So I'm going to start with 10 equals 3x plus 1. And so in this case, I need to know what the x value is, I have a two-step equation to solve. So 10 equals 3x plus 1. Using inverse operations, I'm going to solve for x. The inverse of multiplication is division, so I know that x equals 3. All right, so 310 would be the coordinates there. And as long as you're convinced that it's linear, you'll see a little pattern here. I'm guessing this is going to be 4, but I'm not big on guessing, so I'm going to double check to make sure. We're going to say that the y value in this case is 13. And then we have 3x plus 1. I'm going to solve that two-step equation again. So 13 equals 3x plus 1, nothing to do in the parentheses. I'm going to use inverse operations, and I'm going to figure out what x is. So in this case, I think that x equals 4. And that would make sense. And we knew it would be 4 because those linear graphs follow a pattern. All right, so we call bivariate data. We're going to use substitution to solve for the missing values. Let's take a look here. In this case, our 1 is in the x column, so I'm going to start with the x in the 1 column. And so I know that y must equal 2, right there. And right away we go to the y this time, so 2x equals 4, or 2x equals 4. And we can divide both sides and know that x equals 2. Make sure you're writing down all these necessary steps so that if you need to refer back to your notes, you know what you did and how you did it. Again, we have a 6 in the y column, 2x equals 6. And so inverse operations say we have multiplication, we need to divide. I know that x would equal 3, and that makes sense because we go 1, 2, 3, 4, right in order. And finally, this 4 is in the x column, so I'm going to plug the x in for the substitute the 4 in for the x variable. And so I know that y would equal 8. You can see that the linear model has a nice linear pattern, and the numbers follow right in order in a pattern. Finally, I figure we should probably do one with a fraction on it as well. So I'm going to use the number that I know x is and try to find the number for y. So y equals 1/2 times 8 plus 2. And I wrote 8 as small like that so I could put it over 1. When I multiply my fractions, it's easier to think of them as both fractions instead of a fraction and a whole number. So y equals, I'm going to cross reduce, 4 over 1, which is 4, plus 2. So y equals 6. Alright, and the next one, it tells me what the y value is, so that's where I'm going to put in my y value this time, and I'm going to try to figure out what the x value is. So 5 equals 1/2 x plus 2. I'm going to use inverse operations. And I know that one of my strategies to get rid of a fraction would be to multiply by the inverse or by the reciprocal. And I wrote 2 over 1 here to show that I can cross reduce, but writing 2 over 1 times 3 is kind of silly. 2 times 3 would be just fine, so 6 equals x. Boop, right there. Again, let's take another look, and this time again I have the 4 and it's in the y column, so I'm going to use the y variable to substitute. And I'm going to use inverse operations again. And multiply by the reciprocal is my strategy to get those fractions away from my variable. So x equals 4. Finally, again I have an x value and I need to find the y value. So y equals 1/2 times 2 plus 2. And I really should think of this 1/2 times 2 as 1/2 times 2 over 1. So I can see that that would just be a 1. When I multiply inverses, I get a result of 1. And so y equals 3. And you can see it follows a pattern, 8, 6, 4, 2, 6, 5, 4, 3. So this would be a linear model. Again, all right, so today what I would like for you to be able to do is identify the independent and the dependent variable. The independent is x, the dependent is y. I would like you to be able to find the missing values given a linear model, as well as find missing values given an equation. Okay, so that's it for today.